good morning students. I am Vaishakhi Shah from LJ Institute of Engineering and Technology. Now in last lecture we discussed mouthpiece, external mouthpiece, okay, and now in today's lecture we are going to discuss the different mouthpiece flow through convergent, divergent mouthpiece, okay. So first of all, what do you mean by the term convergent and divergent? So in a convergent divergent mouthpiece, first of all the area of mouthpiece decreases. In convergent part, area of mouthpiece decreases, then after the area of mouthpiece increases. So that is called convergent divergent mouthpiece. And now we are going to derive flow through convergent divergent mouthpiece. So let us start our derivation. For that, refer this diagram first. In this diagram, as you can see, there is a container, or you can say water tank, which is filled up with water, and here in this water tank the atmospheric pressure is acting on free surface of the liquid. As you can see, on the top of the water tank there is a free surface of the liquid, and atmospheric pressure is acting on that free surface of the liquid. Now the mouthpiece is connected to the water tank. Here there are two sections. Consider this diagram here, that there are two sections here, section CC and BB. Here section CC, that is a vena contracta, and BB, that is outlet of your liquid, outlet of a mouthpiece, okay. Here maximum contraction of water jet occurs at section CC, which is called vena contracta, okay. Now in this diagram, consider the center of this, this is your center of mouthpiece, and from center the distance between free surface to center of mouthpiece, which is small h, small h. You can clearly see in this diagram that small h is a distance between free surface of the liquid to center of the mouthpiece, okay. Now here area of jet at vena contracta is AC, and area of liquid at outlet, which is small a, okay. Now we will derive the equation. For that we are applying Bernoulli's equation here. Remember that we are applying Bernoulli's equation for free surface of the liquid. As you can see, this is your free surface of the liquid, and vena contracta, which is your section CC, and exit of the mouthpiece, which is section BB, okay. So if we apply Bernoulli's equation here, then your Bernoulli's equation is P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g plus V2 square by 2g plus Z2. This is Bernoulli's equation. Now we are applying Bernoulli's equation on free surface of the liquid, section CC, and outlet BB. As on the free surface of the liquid, the pressure acting is atmospheric pressure, so P1 by rho g is replaced by HA. So here P1 by rho g equals to HA, and Z1, that is H. From center of the mouthpiece, the water level, the height of water level is H. So HA plus H. Here velocity on free surface is 0. We are considering velocity on free surface 0. So your Bernoulli's equation is HA plus H equals to, now on section CC, Bernoulli's equation at section CC, which is PC by rho g plus Vc square by 2g plus Zc. So here PC by rho g is replaced by Hc, PC by rho g, that is replaced by Hc plus Vc square by 2g equals to, now Bernoulli's equation at section BB, where Pb by rho g, that is HA again, because here at section BB, when water comes out, that is also in contact with atmosphere. So atmospheric pressure is acting on the liquid comes out from BB. So PB by rho g, that is HA, plus V square by 2G, plus here ZB equals to 0. So our Bernoulli's equation is HA plus H equals to HC plus Vc square by 2G plus HA plus V2 square by 2G. This is our Bernoulli's equation on free surface of the liquid, section CC and section BB. Now, as we know that V square by 2G equals to H, and Vc square by 2G, from this equation Vc square by 2G become HA plus H minus HC, make subject V square by 2G and Vc square by 2G. So if cross sectional area at vena contracta and outlet end of the mouthpiece, here we are applying the continuity equation at vena contracta and at section BB. So we are applying continuity equation here for section CC and BB. So your continuity equation become AC Vc equals to A into V. If you remember, then continuity equation was A1 V1 equals to A2 V2. So here at section CC, that is AC Vc equals to A into V. Now though you can write down as A upon AC equals to Vc by V. Now from this equation, if you are making Vc as your subject, then Vc by V become under root 1 plus HA minus HC divided by H. Here from above equation you are making Vc as your subject. So equation of Vc become this. So you can write down Vc by V equals to under root 1 plus HA minus HC upon H. So this is the derivation for discharge through convergent divergent mouthpiece. Now we will solve example based on this theory. First of all, the data is given to you is a convergent divergent mouthpiece having 80 mm throat diameter, discharging water under a constant head of 4.5 meter. Find the discharge through the mouthpiece. Here we have to find out discharge through the mouthpiece, and for that the diameter of the mouthpiece is given to you, which is 80 mm, and head is given to you, which is your H 4.5 meter. Okay. So here H equals to 4.5 meter and diameter D equals to 80 mm. Convert mm into meter, so D equals to 0.08 meter. Okay. Now if you have to find out area, then equation for area of the mouthpiece, A equals to pi by 4 D square. Here we have the value of D, so pi by 4 into 0.08 square. So your answer for area is 5.027 into 10 raised to minus 3 meter square. This is your area, pi by 4 D square. Now we have to find out discharge through the mouthpiece, and we know the equation for discharge through the mouthpiece. Discharge indicated as Q equals to CD into A into under root 2GH. Here for convergent divergent mouthpiece, the coefficient of discharge CD is 1. Remember that. If it is not given into your data, then take CD equals to 1 for convergent divergent mouthpiece. Okay. area, that is small a, and velocity, that is under root 2 gh. Okay, CD equals to 1. So here your answer for discharge, we have different values like area 5.027 into 10 raised to minus 3 into under root 2, g that is 9.81, and h which is 4.5. So your final answer for discharge Q is 47.2 into 10 raised to minus 3 meter cube per second. And if you convert that into liter per second, then your answer is 47.2 liter per second. Okay. So this is your final answer for discharge, which is Q. Now next theory, that is flow through an internal mouthpiece. In last lecture we studied external mouthpiece, which is connected from outside of the water tank, and just we studied convergent divergent mouthpiece. Now our next theory is for flow through internal mouthpiece. Now internal mouthpiece means the mouthpiece which is connected from inside the water tank. This we already discussed this in types of mouthpiece, but the mouthpiece which is connected from inside of the water tank, that is called internal mouthpiece. And the which is also called, internal mouthpiece is also called Boda's mouthpiece or re-entrant mouthpiece. There are two types of internal mouthpiece, where first is running full. As you can see in this diagram, that mouthpiece, the liquid in the mouthpiece touches whole surface, whole area of the mouthpiece, that is called mouthpiece running full. And in this second diagram, this is mouthpiece running free. Here liquid did not touch total surface of the mouthpiece. So this is called mouthpiece running free. Okay. So in internal mouthpiece, which is also called Boda's mouthpiece, and in Boda's mouthpiece there are two types, running free and running full. Now we will solve an example based on Boda's mouthpiece. So here a Boda's mouthpiece of 50 mm diameter is provided on one side of the tank containing water up to height 3 meter above center line of the orifice. Find the discharge through mouthpiece if it is running free. Here type of mouthpiece is running free. The diameter of mouthpiece is 50 mm and the height of liquid from center of orifice, that is 3 meter. So here as D is given into your data, that D equals to 50 mm, so diameter, that is 0.05 meter, and H equals to 3 meter. So you can simply find out area by using equation A equals to pi by 4 D square. Here D, that is 0.05, so pi by 4 into 0.05 square, which is 1.964 into 10 raised to 3. Now discharge through mouthpiece, Q equals to CD into area into velocity. We know the equation for discharge. Now in this case, when mouthpiece is running free, internal mouthpiece running free, for this case the value of CD is 0.5. Remember the different values of CD, which is coefficient of discharge. CD is, the value of CD is different for different types of mouthpiece. Here internal mouthpiece which is running free, for that CD equals to 0.5. So placing the value in the equation, Q equals to CD into area into under root 2 GH, which is velocity. So CD 0.5, area that is 1.964 into 10 raised to minus 3 into under root 2 9.81 into 3, that is your H. So, by solving these values in calculator, you get final answer for discharge Q is 7.53 into 10 raised to minus 3 meter cube per second. And if you convert that into liter per second, then your answer is 7.53 liter per second. Okay. So, this is discharge through Boda's mouthpiece, which is running free. End of this session. Now, in next lecture, we will derive some more theories in our subject fluid mechanics and hydraulics. Okay. Goodbye.